Let us start lecture 36, and today's topic will consider condensed ideal solution, and we will try to look at the graphical presentation of molar partial quantities of components in the solution, as well as we will now look at the common tangent rule, and that common tangent rule will decide the equilibrium between two phases in a system, in a closed system. Okay. So, let us look at that. So, these are two topics, graphical presentation of partial molar Gibbs free energies of components in binary solution, and common tangent and condition of equilibrium between two phases in a system. Till now what we have seen, we have tried to look at the plots of delta G mix, then we have looked at the plot of solution free energy, as well as before mixing what is the unmixed condition free energy of those components. And then we started looking at the pure condition, how the free energies will be placed on free energy versus composition plot. And there also an interesting aspect we have seen, that we can assign a reference value as per our convenience, and we are doing it on the basis of the stable phase that appears for a particular pure metal or pure component A or B at the temperature what we are considering. Okay. And the pressure remains 1 atmosphere now, because in the last lecture itself we have started looking at the condition where pressure remains 1 atmosphere. So, with that basis we will continue our discussion, and we will try to see how the partial molar Gibbs free energies of individual components in a binary solution can be placed over free energy versus composition plot. So, let us take the condition of ideal binary solution, binary condensed solution, and here we are talking about alloy formation from metals, and we have taken A and B metals, and the mole fraction is XA and XB. So, if we add them together, it gives me 1 mole solution. Fine. So, we are keeping temperature at a particular temperature, we are trying to see the free energy plot with respect to composition, and pressure we are fixing at 1 atmosphere, all the time it will be 1 atmosphere. So, these are basically the number of moles of A and B in 1 mole solution. So, that becomes basically the mole fractions also. And we have a equation G2 equal to G1 plus delta G mix. Since ideal, so it can be written as XA GA naught plus XB GB naught plus delta G mix, and this is also can be written as XA GA bar plus XB GB bar. So, when we look at the plot, so we have seen that if this is my delta G mix, this is G1, which is nothing but XA GA naught plus XB GB naught, and for the solution, if I try to plot, the solution plot would be like this. This is G2, okay, and we know how it appears. So, this is G axis and this is XB. And this side is pure B and this side is pure A. So, XA equal to 1 and this is XB equal to 1. Now, this is GA naught this is GB naught. If we consider a temperature T less than TMA less than TMB, so then this too will be considered as for solid, and this is also for solid. Now, we will take this particular picture, this particular plot by considering the reference value as 0. So, since we are taking this temperature which is less than TMA and TMB with reference to this particular free energy versus temperature for pure condition. So, this, let us say this is for B, TMB, and then another one is, let us say this is TMA, and we are taking a temperature here, and if I take that temperature T, or let us say T1, let us say this is at T1, T equal to T1, and if we take those hierarchy, free energy hierarchy, this is G naught A for liquid, this is G A naught for solid, this is G B naught of solid, this is G B naught for liquid. Now, if I look at all those conditions as we have understood in the previous lecture, I can take at T equal to T1 liquid, solid. So, I can take to be 0 and G A naught liquid is greater than G A for solid. So, here also I can take to be 0. So, if I take these reference values and see how this plot modifies. So, we are plotting with the condition that, so this is x b, this is x b equal to 1, a equal to 1, and this is g, and we are taking these two values as 0. So, as per our condition, this will be taken as, at this point this will be taken as G B naught S to be 0, and this will be taken as G A naught S to be 0, fine. And if we consider solid solution at T1, and since it is ideal, that means random solution is possible, all the compositions from 0 to x p is equal to 0 to 1 will get complete miscibility. So, if I try to plot, and at T1 I see that A and B both will be solid under stable condition. Okay. Since that T1 is less than, so this T1 is, here I have to consider T1 because I have taken T1. So, T1 is less than TMA less than TMB, and melting point of B is more than melting point of A, and that is reflected in this particular diagram G versus T plot. This side is T, this side is G, x axis is T and y axis is G. So, from this plot we can see that both A and B solid states will be stable. Okay. So, I can find out G1 before solution making unmixed condition, x A G A naught solid plus x B G B naught solid, and remember, as we have before told that these will be all the compositions also should be considered as solid solution concentration or composition. So, these are solid. So, since these two quantities are 0, so G1 would also be 0. So that means this particular this is nothing but G1, or let me just put it this way, this is nothing but G1. So G1 all composition, it will lie over this 0 line. So let me just show then G2. G2 solution is G1 plus delta G mix. So I can, this would be 0 plus delta G mix. So if I try to look at delta G mix plot would be this. It will be symmetric since it is minus T del S mix, delta G mix. So now G2 would exactly fall on delta G mix because G1 is 0. So if I try to plot G2, so G2 would be exactly falling on this particular delta G mix point. So I have given a little gap just to showcase that, just to make a difference between these two color, okay, but they are actually falling on the same point. So same line actually, delta G mix, same curve. So this is nothing but G2 for the solution. Okay. Now we have already found out delta G of B as well as A when it is in the mixed condition, that is the partial quantities. So how did we do that? So we actually taken, for example, at this point this composition I have to find out partial mixing quantities. So I have to draw a tangent there. Okay. So that tangent over that delta G mix plot, so then this quantity is nothing but delta G B bar M, and this quantity is nothing but delta G bar M A. So, and if you go back previous lectures, you can find out how we did that graphically. That particular tangent over any point of delta G mix, that tangent wherever it cuts on the pure condition x b equal to 1 and x equal to 1, from 0 till that point, that particular value will be considered as partial quantities of A and B when they are mixed in the solution. So delta G mix, let us say this point corresponding to A point at A would be equal to delta x A delta G A bar M, and this is for solid, this is solid, plus x B S delta G bar M B for solid. Okay. And this is of course for solid. So I can actually put it like this, G2 x A solid delta G bar A solid plus x B solid G bar B solid. So this composition is nothing but x A solid and x B solid. So those are these two compositions. Now since G1 is 0 at all the compositions starting from 0 to 1, if I consider with respect to B, so then this G2 lies exactly on delta G mix plot. So these two would also be similar to G A B, as well as this would be equal to G A bar. Okay. So that means in this particular condition with respect considering these two reference conditions, we can see that common tangent over the solution line, wherever it cuts those pure condition over g axis, that means the y axis. So, that particular distance from 0 in this particular situation becomes my molar partial quantities. So, considering that 0 reference, it becomes very easy to me to visualize how that g bar A as well as g bar B are placed on this free energy versus x plot, which is also nothing but the mixing partial quantities. So, this is one part. Now, if we try to look at temperature T equal to, let us say T3, let us say I take T3 as this temperature T3. So, still there also I can get the similar conditions, exactly similar conditions. Of course, the values could be little different for delta G mix away from x a equal to 1 and x b equal to 1, but there also I can assign this 0 value as G A naught liquid, and here I can assign G A B naught liquid. Why? At temperature, this is at T equal to T3, this is at T equal to T3 equal to 0 equal to 0. Fine. How? Because at T3, if I try to look at the free energy hierarchy, G A naught solid is greater than G A naught liquid, because at T3, which is greater than T M A and greater than T M B greater than T M A, liquid A would be stable at T3, since it is more than melting point of A. So, that time I can consider G A naught liquid to be 0, and for the B still it will be. So, then I can take would be 0. So, since we are considering that, and here we are taking liquid solution, and from liquid A and B, both are liquids. So, that time every composition will have to be considered as liquid composition, and every quantities, free energy quantities, whether pure or partial, to be taken as liquid. So, all those places you just replace S by L, so you will get those conditions. And here also you will see that G1 for solid would be 0, because we have considered this one, two quantities are 0. So, actually G1 becomes X A liquid, G A naught liquid plus X B liquid, G B liquid. So, these two quantities are 0, we have assigned 0. So, it becomes 0. So, exactly it will be falling on the 0 line, similar type of plot like this. G2 would be G2 liquid now would be equal to delta G mix liquid. Okay. So, like that way, similarly we can see that we can get G A for solid, G A bar for solid solution and G B bar for solid solution in the previous case, but here also we can get, instead of solid now, these are all cases we have found out solid. The similar graph will give me G A bar liquid, G A bar liquid, as well as the same will be given as G B bar liquid solution. So, this is, remember, not, this is liquid solution. In the liquid solution, molar partial Gibbs free energy of A in the liquid solution, as well as molar partial Gibbs free energy for B in the liquid solution. Similar plot will look like. But now situation could be different without taking any assigned value. Okay. So, if we consider that, let us not take any assigned value, like it can be any value for for let us say a condition, solid condition, what we have taken here in this case, let us say in this case, let us take a situation, we are making a solid solution. Let us take a solid solution, and then from solids, let us say that solid A and B, and G A naught solid and G B naught solid are not equal to 0, still that case is also we can find out what will be the partial molar quantities of A and B in the solution. So, now it will form a solid solution. So, I will just plot that. Okay. So, this is G, this is X B, pure B, and this is pure A. So, X A equal to 1, X B equal to 1. So, we are considering binary solution all the time. Now, we are not assigning these two values as 0. So, we can take G 1 like this. This is G 1 equal to X A G A naught plus X B G B naught. Okay. And the free energy plot, let us say like this. Okay. So, this is G 2. So, let me plot G 2 separately without giving a reference to G 1. So, I can take this plot here. So, let me draw a tangent at this point. This is X B equal to 1, X A equal to 1, this is X B is varying like this, this is G, this is G, this is also G. So, now at this point if I draw a tangent, the tangent will be passing through this. So, let us say this is G 2. Okay. So, this particular point, let us consider this as C, or composition, let me just mark it as C. I can draw a parallel line passing through this point with respect to composition axis. A parallel line is drawn, and then one vertical line with respect to G composition axis I can draw like this. Now, this particular point let me consider as G, let me consider as G prime B, this is considered as G prime A. Okay. I do not know whether these two are actually partials. I am just taking a free energy value which are cutting, this common tangent is cutting across the pure component side. Now, this particular, all those points, let me mark it. So, let me mark it that this is A, this is B, this is C, this is D, this is E. Okay. And now, I can draw a parallel line with respect to B here. Another parallel line is drawn. So, this point let me consider as F. Okay. Now, I could see that this point is nothing but G B prime, and this is C is basically G 2 at composition at point C. So, this will be also, this point will be G 2 on the free energy axis. So, now let me look at the slope of this green line, which is the tangent line. That slope will be decided if I consider A to be the reference. So, this is my theta, let us say the angle, the slope of that particular tangent. So, this would be equal to this is also theta, geometric rule if we follow, and then I can write. Now, with respect to this consideration, all those angles as well as the parallel and vertical lines, I can take the slope of this particular angle BAC with respect to XA. So, it becomes BC by BA. So, this is nothing but DG2 dXA at C point. Okay. Similarly, if I consider the angle FCE, and here I am taking with respect to XB, okay. So, that time I can take FE divided by FC. So, this is nothing but DG2 dXB at point C. Okay. So, now I could see that both the angles are similar. So, these two are equal. Fine. So, then I can write DG2 dXA equal to DG2 dXB at point C. So, now equal to FE divided by FC. So, FE is nothing but GA prime minus G2 divided by FC is nothing but XB at point C. Since if this is XB, from this side if I try to calculate, so then it will be, or if I try to calculate the composition from 0 XP with respect to XP, so this would be my XP, and if I try to calculate XA at the C point, so this is at that C point, XA would be starting from other end, starting from XA equal to 0. So, this is XA equal to 0 and XB equal to 0, these two parts, two sides. So, then I can write, so it is basically DG2 dXA. So, I can write DG2 dXA equal to GA prime minus G2 divided by XB. So, GA prime minus G2 equal to XB at point C. So, GA prime would be equal to G2 plus XB XA. So, at point C. So, now you could see, and previously if we recall, previously we have found the partial quantities GA bar would be equal to G2, if I consider G2 is the solution free energy, plus XB dG2 dXA. So, that means this is nothing but the partial molar Gibbs free energy of A in the solution, and that actually falls on the same point where GA prime is obtained. So, here if I look at this particular plot, so this would be nothing but GA bar. Okay. So, here also I could see that the common tangent over any point on G2 line, that common tangent wherever it cuts on x equal to 1 on the free energy axis, that particular value is nothing but GA bar. Okay. We can prove for the GB bar also. So, this B point, if I take only the free energy part, that can be taken as GB prime. Okay. So, now if I look at for calculation of G B prime, I can take this angle dg2 dxa with reference to A. I can write this one as, if I see here, BC by BA, BC by BA. So, here I can, BC is nothing but G2 minus GB prime, and BA is nothing but minus of AB, or I can write G2 minus GB prime minus XA. So, let us see how it comes. You see, this point is now becoming XP bar. If I take only the free energy part, this is G2 and XA to be considered in this direction. So, that means we have taken BA. So, that means if I consider AB, then it has to be minus of XA at point C. At point C, so this is at point C. So, this is nothing but dg2 dxb. So, then dg2 dxb equal to g2 minus gb prime divided by minus xa. So, we get g2 minus gb prime equal to xa minus dg2 dxb. So, it comes out to be gb prime equal to g2 plus xa dxb. We have already seen before Gb bar is nothing but solution free energy plus Xb Xa dg2 by dg2 dxb. So, hence Gb bar is nothing but Gb prime. So, this is Gb bar. So, the partial molar gives free energy of B component in the solution at that temperature and pressure. So, we can see that this point is nothing but with the cutting point of that tangent at any point over G2 line. Wherever it cuts the free energy axis at xb equal to 1 should be considered as partial quantities. Fine. So, now you can see, even if you do not consider GA, this is GA naught, this is GB naught. Okay. So, for they are not to be 0. So, still we can see that the common tangent drawn on any point over the G2 line will cut the pure component side. That free energy is nothing but gives partial molar gives free energy of those components in the solution. So, let me stop here. Now, we will be dealing with this molar partial free energies of A and B in the solution and try to look at the equilibrium concept when two phases are existing. Okay. So, let me stop here. We will continue our discussion in the next lecture, where we will try to look at the equilibrium part, considering this molar partial gives free energy of A and B in the solution. Thank you very much.